everyone. In this video, we are going to work through 4 examples where we are computing a derivative, but we are using implicit differentiation. So for example A, we have y cubed equals 2x, and we want to find dy dx, the derivative of y with respect to x. So we're going to begin by computing the derivative with respect to x of both sides. So that's going to look like this, the derivative with respect to x of the left side of the equation, which is the y cubed, and then the derivative with respect to x of the right side of the equation, which is 2x. So now we actually need to compute the derivative, and what is important to remember here is that when we're looking at a term that is a term containing a y, but we're computing the derivative with respect to x, that we have to make sure that we use the chain rule here. So if you want to kind of think of this as the inside and outside functions like we did when we did the chain rule, you can kind of think of the outside function here is something getting cubed, and my inside function is y. So when we compute the derivative of something cubed, that's going to be 3 something squared. But when we compute the derivative of y, because we're taking the derivative of y with respect to x, the derivative of y is dy dx, which you could write as y prime. I'm going to go ahead and be in the habit of writing dy dx because I have found so many times my students or even myself will miss the little prime symbol in my work and then make a careless error because of that. So the derivative of the y cubed term will be 3y squared, and then we chain on the derivative of y with respect to x, that's the dy dx. Now looking at the second term, our second term on the right-hand side of the equation is in terms of x, and we're taking the derivative with respect to x. So that does not require the chain rule. The derivative of 2x is just 2. And then we want to solve for dy dx. So in this case, we'll go ahead and divide both sides by the 3y squared. So we'll end up with 2 divided by 3y squared. That's going to be the derivative of y with respect to x. Let's look at example B. X squared times y squared is equal to -7. So we always start the same way. We want to compute the derivative of each side. So the derivative of everything you have on the left, and then the derivative of everything that you have on the right. So that's the derivative of the x squared y cubed term, and then the derivative of -7. But now we have to be really careful on the left-hand side here because we have to recognize that we have a product. So this is going to require the product rule. So you can start to see how we start to add in all of these previous rules that we've learned. They kind of all come together here as we're using implicit differentiation. So a little review of the product rule. Remember, if we have a function that is a product of f times g, and we want to find its derivative, we take the first function times the derivative of the second function plus the second function times the derivative of the first. And so that's exactly what we're going to do here. We're treating the x squared term as my f of x function in the product, and then the y cubed term is my g of x in the product. So let's do our product rule. So the first is going to be the x squared times the derivative of the second term, and our second term is this y cubed. But again, that's a term that is in terms of y, that contains a y, so this is where we have to use that chain rule again. So the derivative of y cubed will be 3y squared, and then we have to chain on the derivative of y with respect to x. So that's the first function times the derivative of the second, plus the second function is the y cubed, times the derivative of x squared, which is just 2x. So that is my product rule. And let me just underline again in case you need it. We're looking at my first term here. This is the f term, and then this is my basically g prime. So that's f times g prime plus my second term. Y cubed was my g term times f prime there. That's my product rule. Now on the other side, the derivative of -7, since that is a constant, will just be 0. So I'm going to reorder these terms first. I'm going to make the 3 come in front as a coefficient and write this as 3x squared y squared times dy dx plus 2xy cubed equals 0. And then remember, what we're trying to solve for is the derivative of y with respect to x. So we want to basically isolate the dy dx term. So you are essentially going to subtract. There we go, try again. We're going to subtract the 2xy cubed term and then divide. So our derivative will equal -2xy cubed divided by 3x squared y squared, which of course we can simplify. So dy dx, if we divide out the x's, and we can divide out a y squared into that numerator, it looks like we'll be left with a -2y in the numerator. There we go. Divided by a 3x there in the denominator. So we have -2y divided by 3x for dy dx. Example C, sine of y cubed equals x squared plus 2y. So again, we're going to take the derivative of both sides with respect to x, everything on the left side and everything on the right side. And if you recognize that we have a sum on the right-hand side, and so you want to go ahead and basically use that sum rule for derivatives, where you're recognizing that you can compute the derivative of those two terms separately, that would be completely fine. So we're taking the derivative of the sine of y cubed, and then on the right side, the derivative of x squared, and then the derivative of 2y. Now, we have to be really careful here because sine of y cubed is definitely a composite function, so we need to use the chain rule here. But this is a composite function that actually has 3 parts. This is one of those that I sometimes call an onion because it has so many layers. So if you think about the outermost layer being your function f, that's going to be the sine of something. And then inside the sine function, we have something cubed. And remember, I'm writing something cubed instead of y cubed because I'm treating y like it is some unknown function that's in terms of x. And then inside of the something cubed, I have my innermost layer, which is what I'll go ahead and call y. So the derivative of sine of something is cosine of something. And then the derivative of something to the third power is 3 times something squared. And then the innermost layer, the derivative of y with respect to x, will be our dy dx. So that's how I am tackling this first derivative, the derivative of sine of y cubed. So we're going to end up with the derivative of the outermost piece. That's going to be the derivative of sine of something, which is cosine of something. And then, of course, what I'm putting inside there is the 2 inner layers. And I didn't need such a big parenthesis there because really what I'm putting inside of there is y cubed. So we'll have cosine of y cubed. Okay, then chain rule. So if you think about it, like I've done the derivative of the outermost layer. Now next I have the derivative of the inside, the second layer, which was something cubed. That's 3 something squared. In other words, that's 3y squared. So now I've taken care of the derivative of the second layer. And then I multiply with the chain rule one more time, the derivative of the innermost layer, which is the dy dx. So that is the chain rule with a composite function that has several parts. Moving on, we've got the derivative of x squared. And that x squared term, that's in terms of x, so that's just going to be 2x. And then lastly, we have the derivative of 2y. So once again, that's a term in terms of y. It has a y variable in it, but we're taking the derivative with respect to x. So that's going to be 2 times the derivative of y with respect to x. Looks something like this. So now when we have all of these terms, it's helpful to identify how many terms we actually have. So we have this big term here on the left, and then we have 2x, and then we have 2 dy dx. And 2 of these terms have the dy dx that we want to basically solve for. So I'm going to reorder this very first term. I'm just going to bring this the 3y squared in front, and write this as 3y squared times the cosine of y cubed dy dx. So I'm going to reorder that. I'm going to also subtract the 2 dy dx term over, so I can have those dy dx terms on the same side of the equation, which then is going to let me factor, because now I have a common factor. So we'll factor out the dy dx. So we'll have 3y squared times cosine of y cubed minus 2 remaining, and that will be equal to 2x. And then finally we can divide. So dy dx will equal 2x divided by 3y squared cosine of y cubed minus 2. And then we'll look to see if we can simplify, but it looks like we can't. We don't have any common factors. So this is the best, most simplified answer for dy dx. All right, last one. Hopefully we're getting a little bit more comfortable with implicit differentiation. The derivative of cosine of x squared plus y squared is equal to 3y to the fourth. Now, at this point, now that we've done several examples, if you're comfortable kind of skipping that very first step where we wrote out that we were taking the derivative of everything on the left and everything on the right, then please do so. I encourage you to try to streamline a little bit if you feel comfortable with that. So I'm going to show that in this example. However, we have to recognize here that we have a composite function. So this is definitely composite. And anytime we have the composite functions, we know we're going to have to use the chain rule. So for this one, we're looking at, let me identify all of my pieces. My outer layer is the cosine of something, and my inner layer is the quantity x squared plus y squared. So when we do our derivative, the derivative of cosine of something will be negative sine of something. And then when we compute the derivative of x squared plus y squared, that has 2 terms. So I'm going to do the derivative of each term separately. The derivative of x squared will just be the 2x, but the derivative of y squared will be 2y times the derivative of y with respect to x. So we have another little chain rule that happens inside there. All right, so moving on, the derivative of cosine of something is negative sine of something, and our inner function is the x squared plus y squared. Then we chain on, so we've done f prime, then we chain on the derivative of the interior function. So that's going to be 2x plus 2y dy over dx. Now the right-hand side, we have 3y squared, and that again is a term containing a y. So the derivative of 3y squared will be the 12y cubed, and then we'll chain on the derivative of y again with respect to x. Now, because this second quantity, this 2x and this 2y dy dx, this is 2 separate terms, we need to go ahead and distribute this negative sine of x squared plus y squared, which I know looks pretty complicated. We're just distributing. So I'm going to distribute, but also I'm going to reorder. So I'm going to pull that 2x and write that in front. So negative 2x times the sine of x squared plus y squared. And then that would be negative 2y dy dx times the sine of x squared plus y squared is equal to the 12y cubed dy dx. So now I can clearly see that I have 3 distinct terms here. And again, we want to get the terms that contain a dy dx on the same side. So we'll leave the negative 2x sine of x squared plus y squared where it is. And we're going to basically add the other term over. So we'll have a 12y cubed dy dx, and then we're adding this 2y dy dx sine of x squared plus y squared term to the other side. which then is going to let us ultimately factor. So we're going to factor out this dy dx from the right-hand side, and we'll be left with a negative 2x sine of x squared plus y squared is equal to dy dx times the quantity 12y cubed plus 2y sine of x squared plus y squared. And finally, we can divide and isolate the dy dx. So pretty ugly looking answer. Negative 2x sine of x squared plus y squared, all divided by the 12y cubed plus 2y times the sine of x squared plus y squared. Nasty looking answer, but we made it. And as I look at this, technically, I think I put a box around it, but we could simplify. So we technically could divide a 2 into the 12 and into this 2 down here. So a more simplified answer would be the negative x sine of x squared plus y squared, all divided by 6y cubed plus y times the sine of x squared plus y squared. I was a little excited to be done, as I'm sure you were too. So what I have in blue here is technically the most simplified answer possible.